Good morning. Today is the week 2 of the 11 practice session for the NPTEL course, an introduction to climate dynamics, variability and monitoring. So last class we were discussing some basic terminology such as climatology, frequency, extremes, normals, etc. Then we also did some basic calculation based on radiation loss. We calculated what is the maximum wavelength at which the sun emits radiation, what is the maximum wavelength at which the earth emits radiation, and we also calculated the temperature of the earth from the Stephen Boltzmann law. And we also learned what are the different layers of the atmosphere, composition of the atmosphere, etc. And during the last class, someone asked me about the impact the climate change has on pathogens. So it was written in your NPTEL material. So someone asked me about the question. So I thought today we'll start with just clarifying the question. So climate change is known to affect the spread of viral and bacterial pathogens. Pathogens refer to a wide range of disease agents, including virus, bacteria, germs, and fungi. And this climate change impact these pathogens directly through influencing their survival, reproduction, and life cycle, also indirectly by influencing their habitat, environment, or competition of pathogens. Now let's see how different meteorological parameters are actually affecting the production, survival, and all these things of certain pathogens. So a pathogen, so first we will look at how temperature is influencing. So a pathogen needs a certain temperature range to survive and develop. So rising temperatures can influence the reproduction and extrinsic incubation period of pathogens. And extended periods of hot weather can raise the average temperature of water bodies and food environment, which will create a favorable environment for microorganism reproduction cycle. So that's how temperature influences pathogens. So there are certain pathogens which are actually capable of being produced in the changing temperature. Some pathogens cannot survive also at an increase in temperature. So maybe some new pathogens may develop, and some pathogens may it will be difficult for them to survive as well. So both things can happen due to increase in temperature. Now, how rainfall is affected? So rainy season we know is already related to an increase of fecal pathogens, because the heavy rain basically stirs up the sediments in the water. So rainfall basically plays an important role in the development of waterborne disease pathogens. So when rainfall happens, it stirs up the sediments in the water, which basically lead to the accumulation of fecal organisms. And unusual precipitation after a long drought can result in an increase of pathogens, which basically result in a disease outbreak. Also, droughts or low rainfall, which basically lead to low river flows, and it results in the accumulation of such waterborne pathogens. Similarly, other parameters such as sunshine, winds, and humidity also have similar effects. So I have just given the source of this paper. So I have taken all this from a research paper. So if someone wants to know more about these things, you can always go and have a look at the paper. So I have just given the link of the paper. It was basically a review paper. So this is just a schematic that shows how climate change is affecting the transmission, habitat, and susceptibility of different pathogens. So how the climate change affects such as heat, drought, storms, wind, fire, and all are affecting all these the habitat, the transmission, and the development and evolution of new pathogens, and also their susceptibility. So how it is influencing. This is just a schematic which basically shows that. So I think you have got a basic idea on how climate change spread and production of pathogens, and evolution of new pathogens. So now let us go through some problems. We'll just solve some problems which are related to the things that we learned in the last class. So the first question is, what does the term normals refer to in climatology? The options are: it refers to extreme weather events, variability range of weather variables, mean or expected values of weather variables over long periods, rate of incidence of extreme weather phenomena, mean or expected values of weather variables over short periods, the standard deviation of weather variables over a specific period. So we learned what is normals in the last class. So normals is basically mean or expected values of weather variables over long period of time, not short period. So it is a mean or expected value of weather variables like temperature, precipitation, etc. over long period of time. So normals is basically the mean or expected value of weather variables over long periods. For example, 30-year average or moving average of yearly precipitation, temperature, etc. over a geographic location. Now the second question is, how the concentration of carbon dioxide in the atmosphere has changed since 1750. So it has decreased significantly. It haven't undergone any change. It is remaining constant. Then it has increased significantly. Then it is fluctuating randomly. And then it has decreased initially and then sharply increased. So like we know that it has basically increased significantly. So this is a figure which shows the increase in carbon dioxide over the last 200, like 1715 to 2020. So as we can see, before industrial revolution or during the pre-industrial time, the amount of carbon dioxide present in the atmosphere was around 278 parts per million, whereas in the recent period it has almost doubled, showing an increase of with a current level of carbon dioxide concentration of around 416 parts per million. So there is almost 50% increase, and the not double, there is a 15% increase in the carbon dioxide present in the atmosphere. So the answer is increased significantly. Which of the following are zones that least influence climate? So we also learned about the different spheres which basically influence the climate. Troposphere we know as the lowest layer in the atmosphere. Hydrosphere is where the water is present in liquid form. And we have the mesosphere, which is basically one of the top layers of the atmosphere. Water is present in solid form. Then we have the biosphere, where all the living organisms are present, including us humans, animals, plants, etc. and we have the lithosphere, which is uppermost layer of the earth where we all reside. That is the lithosphere. Now the question is, which of the following are zones that least influence climate? No, the answer is mesosphere, which is the top layer of the one of the top layers of the atmosphere, which is like at a height of 50 to 80 kilometer, very far from the surface of the earth, because of which it has very least influence on Earth's climate. So mesosphere is the answer. And the fourth question: how does climate change affect agricultural production? Four options are there: increase in crop yield, rise in crop failure, expansion of arable land, decrease in water availability for irrigation. These are the four options. We know the climate change is leading to, and climate change is leading to prolonged drought conditions and increased extremes, etc. So all these things affect the agricultural production. So prolonged drought conditions leads to decrease in water availability for irrigation. Also, like extreme rainfall and all can lead to crop failures as well. So both could be the climate change is basically leading to enhanced rise in crop failures, also decrease in water availability for irrigation. Now, so we learned like there has been a 50% increase in the carbon dioxide concentration over the earth. So like from approximately 200 parts per million, it has increased to approximately 400 parts per million. So how it has actually affected to the increase in temperature? So the mean, along with this, how much the global surface temperature has increased by how many degrees Celsius over 1850 to 2010. So if you remember, we learned this graph in the last class. So as we can see from the figure, during the period 1850 to 2020, this basically shows the anomaly with respect to the climatological mean. So if you look at the value, there is from 0, there is a rise up to approximately 1.2 degree Celsius. So 1.2 degree Celsius is the correct answer. So the mean global surface temperature has increased by about 1.2 degree Celsius during 1815 to 2020 with respect to the climatological aspect. And we talked about carbon dioxide concentration. There was a 50% increase. Along with this, we are facing an increase in temperature of around 1.2 degrees Celsius globally. Now, what is meant by the term lapse rate? So I think we discussed about this term when we were discussing the different layers in the atmosphere. So we told that in the sorry, I have a little bit of cold, so please bear with me. In the troposphere, since so if you remember, we discussed that the Earth is almost transparent to the incoming solar radiation. Not the Earth, sorry. The atmosphere is almost transparent to the incoming solar radiation. And the atmosphere gets warmed by absorbing the outgoing long wave radiation which is being emitted from the Earth. And we calculated what is the wavelength range and all. And we saw that the incoming solar radiation is mostly in the short wave range of the spectrum, mostly in the visible range. And the long wave radiation that was going from the Earth was in the long wave range or infrared region. So it's like outgoing long wave radiation. So since the atmosphere is mainly heated by the outgoing long wave radiation from the Earth, in the troposphere, when we look at the temperature from that, we can see that the temperature is actually decreasing with respect to height as we move away from the surface of the Earth. So this rate of decrease of temperature with respect to altitude is known as the lapse rate. So this is the rate of decrease of temperature with respect to altitude, not pressure, not humidity, not carbon dioxide. So basically the rate of decrease of temperature with respect to altitude, and this happens in the troposphere. The value of gamma rho T by rho Z or dt by dz is given by minus 6.5 Kelvin per kilometer. From the surface of the Earth, if we go to 1 kilometer height, there will be minus 6.5 degrees Celsius decrease in temperature from the surface temperature. Ts minus 6.5. Surface temperature is given by Ts. After you travel, after you go up to the height of 1 kilometer, there will be a decrease of temperature by minus 6.5. Now, the correct sequence of different layers of atmosphere from the surface of the Earth upward is given by, as we know, we discussed. Yeah. So the lowest layer in the troposphere, which is having decrease in temperature with respect to height, and the value of lapse rate is minus 6.5 degrees Celsius per kilometer, minus 6.5 Kelvin per kilometer. Then from 11 to around 50 kilometers, we have the stratosphere, which is where the temperatures are actually increasing with respect to height due to the presence of ozone. Then above the stratosphere, we have the mesosphere, where again the temperature is decreasing with respect to height. And then finally, we have the thermosphere. So troposphere, stratosphere, mesosphere, and thermosphere. That is the correct troposphere, stratosphere, mesosphere, and thermosphere. In the troposphere, temperature decreases with respect to height. Stratosphere, temperature increases with respect to height. Mesosphere, again the temperature decreases with respect to height. And thermosphere, temperature increases with respect to height. The coldest layer in the atmosphere, the coldest region in the atmosphere is the mesopause, which is actually at a temperature of minus 80 degrees Celsius and at a height of 80 kilometers. So mesopause is the coldest region in the atmosphere. We just now only we told in the stratosphere the temperature is actually increasing with respect to height. So I told like this is caused by ozone molecules, which uh, radiation is actually the ozone molecules absorbing. So I think once you know ozone, then two options: infrared and ultraviolet. So which particular wavelength is actually ozone absorbing? So ozone basically absorbs the ultraviolet region of the spectrum. So even though we know that the lambda max of the solar radiation is in the visible range, it doesn't mean that the sun emits radiation only in the visible range of the spectrum. It emits radiation in all wavelengths in the electromagnetic spectrum. But the maximum radiation, maximum amount of radiation is being emitted in the visible range. Still, it emits radiation in all wavelengths. So the ozone molecules present in the stratosphere basically absorb the ultraviolet radiation coming from the sun and then lead to the increase in temperature with respect to. Given the tropospheric lapse rate is 6.5 Kelvin per kilometer and the near surface atmospheric temperature in Delhi is 305 Kelvin, the temperature at an altitude of 2 km above Delhi is dash Kelvin. This is the question. So in the question, the lapse rate is given, which is 6.5 Kelvin per kilometer, and the surface temperature in Delhi is given, which is 305 Kelvin. You need to find the temperature at Z is equal to 2. Z is equal to 2 will be surface temperature minus 2 into 6.5. How much will be the value? The answer will be 291 Kelvin. To get a better picture, you can write it in Celsius also. In Delhi, the surface temperature was 31 degrees Celsius, but at an altitude of 2 km from the surface, the temperature reduces to 18 degrees Celsius. Which of the factors influence the mean annual surface temperature at any location of the world? Select all that apply. The first option is altitude. So we know that as the distance, as the altitude increases, the temperature also, the temperature kind of decreases. So altitude obviously influences the mean annual surface temperature. Second one is latitude. Does latitude has an effect on the surface temperature over a location? So if you see, so this is the latitudinal distribution of surface temperature during the month January. So you can see high temperatures in the equatorial region of around 30 to 35 degrees Celsius. And as we go up along the latitude, or as we move up in the latitude, we can see the temperature is decreasing. And over the polar regions, the temperature is decreasing up to minus 20, minus 25 degrees Celsius. So from the 35 degrees Celsius temperature experienced in the equator, temperature reduces to almost minus 20, minus 25 over the polar region. So that much decrease is happening with respect to latitude. So latitude is correct. Now the third one is time of the day. We know that there is a diurnal variation in temperature, which means if you plot temperature with respect to hours in a day, you can see it will be like this. The peak will be obtained at around 15 hours or something. Just 3 p.m. in the afternoon, and during night time you will get very low temperatures. So this is how the temperature varies. So within a day, obviously there is changes in temperature with respect to the hour in which we are calculating. But the question is, the mean annual surface temperature at any location of the world is influenced by these factors. So since we are considering annual surface temperature, we are averaging like at all hours of the day most probably. So this kind of it will be like averaged out. The variations will be averaged out. And the fourth one is season. So does season has an influence on the temperature experienced over it? We know that during winters we experience uh, lower temperatures, and during summers we experience higher temperatures. So this, as I said, this is the latitudinal distribution of temperature during January, and this is the latitudinal distribution of temperature during July. So as you can see, high values of temperature can be seen during over the equatorial region, which is as high as 35 degrees Celsius. So if you look at India, during the January, the Indian region received a temperature of around 20 degrees Celsius, whereas during July it has increased to 25 to 30 kind of during that range, which is like mostly summer period. So there is this much variation in temperature as the seasons change. So obviously there is seasonal variation in temperature. But here again the question is annual surface temperature. Mean annual surface temperature. So annual means we are averaging all seasons as well. So in that case again seasonal changes will also be averaged out. So since we are considering annual surface temperature, altitude and latitude will be now. This is a new method. Question is, if the atmospheric pressure is 101.3 kilopascal, then the question pressure is given 101.3 kilopascal. Temperature is also given 25 degrees Celsius. What is the density of the air using ideal gas law? So they have already told to use the ideal gas law. We know the ideal gas law is given by PV is equal to nRT, right? So this is the ideal gas equation which we all are familiar with. We have been using since whole time. So here we know P is basically pressure, which is expressed in Pascal or Newton per meter square. Pressure is basically force by area. Then V is the volume occupied by the gas, which we generally express in meter cube centimeter, meter cube, like in a side. And T is the temperature, which is expressed in Kelvin. We have N, which is the number of moles of the gas that we are considering. And we have R, which is the ideal gas constant, which is having a value of 8.314 joule Kelvin inverse mole inverse. The question is trying to find the density of the air. Which we can represent using rho. So this is not given in the question, right? So we need to introduce rho in the equation. So we know that density is equal to mass by volume. So we can write volume is equal to mass by density, right? So the equation becomes, instead of P we will give mass by P into M by rho is equal to nRT. P M by rho is equal to nRT. We can write P M is equal to n rho R. Suppose we are considering 1 mole of an ideal gas, then M will be the molar mass of the gas that we are considering. So in this case, the gas that we are considering is atmospheric air. Dry atmospheric air. So if you remember, so how can we find the molar mass of the atmospheric air? So if you remember, in the last class, we learned about the composition of the atmosphere, right? So we know that the atmosphere consists of 78.08% of nitrogen, 20.95% of oxygen, and 0.93% of argon, right? So from this, we can calculate the molar mass of atmospheric air. The molar mass is given by 78.08 divided by 100 into molar mass of nitrogen as 28. 14 is for nitrogen atom, 28 is for the molecule, plus 20.95 by 100 into molar mass of oxygen is 32. 16 is for atom, 32 is for the molecule, plus 0.93 by 100 into argon. Argon is having a molar mass of 39.95. Correct? So since we know the composition of the atmospheric air, we can calculate the molar mass of atmospheric air, which contains 78.08% nitrogen, 20.95% oxygen, and 0.93% argon. Now if we calculate the value, we will get 78.08 will give a value of 28.93 gram. The molar mass of dry atmospheric air is 28.93 gram. Now, if we substitute it in the equation, it will This is in gram. So in the equation we have to substitute it in kilogram. Is equal to N will be 1. So rho R into D. So whenever we are considering dry atmospheric air, this value of M will be a constant. So we can redefine the value of, we can redefine a new constant R star, such as R by molar mass of air, which is 8.314 joule Kelvin inverse mole inverse divided by 28.93 into 10 raised to minus 3 kilogram per value will be 8.314 divided by 28.93 into 10 raised to minus into 10 raised to 3. The answer will be 287 joule Kelvin inverse kilogram. This will be the answer. So whenever you are using the ideal gas law for dry atmospheric air, instead of the R value 8.314 joule Kelvin inverse mole inverse, which is for 1 mole of any ideal gas. In case of dry atmospheric air, R will be 287 joule Kelvin inverse kilogram inverse for 1 mole of dry atmospheric air. And we have density instead of volume. So P is equal to rho R. Now, what was the question? The question was to find the density of the air. The pressure is given as 101.3 kilopascal. Temperature is given as 25 degrees Celsius. We need to find rho. So now we have our new equation. P is 101.3 into 10 raised to 3 Pascal. This will be 25 plus 273, which will be 288, 298, 273 plus 25 will be 298. 298. So if you substitute, so we can substitute rho is equal to P by R, where P is 101.3 into 10 raised to 3 Pascal divided by R is 287 into T, 290. Okay, what will be the value? The answer will be 1.18 kilogram per meter. This is the density of the dry atmospheric air. So that is the answer to the question. So just remember, for 1 mole of dry atmospheric air, the equation reduces to P R is 287 joule Kelvin inverse kilogram inverse. Okay, now just give me a second. So we learned how the temperature is changing with respect to height, right, and the atmosphere. And based on the thermal structure of the atmosphere, we have 4 different layers. Now let's see how the atmosphere, what is basically atmospheric pressure when we talk about the, yeah, what is basically atmospheric pressure and also how the atmospheric pressure is changing with respect to height. Okay. So we know that the basic definition of pressure is force exerted per unit area, right? Pressure is given by force by area. Now, what is atmospheric pressure? So in case of atmospheric pressure, the force is basically the weight of the atmospheric column present above that particular height. So if we are defining the pressure at a height z, then the weight of the atmospheric column lying above that particular height z is a force exerted on that column. So the force divided by area gives you the pressure. So atmospheric pressure at any particular height in the atmosphere is the weight exerted per unit area by the atmospheric column lying above that. Okay. So atmospheric pressure at any particular height in the atmosphere is the weight exerted per unit area by the atmospheric column lying above that particular height. So the weight or the mass of the atmosphere, which we can represent using the density of the air molecules present in the atmosphere, decreases exponentially as we go up in the atmosphere. Since pressure is basically the weight or the amount of air molecules present in the atmosphere, as we go up in the atmosphere, Similar to the density of the air molecules, pressure also decreases exponentially. So as you can see the representation, like in the surface there is very denser molecules are present, but as we go up it is becoming rarer and rarer. Now just to get an idea how it is, the values, how it is changing. So if you look at the surface we have a pressure of almost 1000 hectopascal, and then we go up to a height of 6 kilometer itself, the pressure has decreased by half. So at a height of 5 kilometer itself, we have a pressure of 500 hectopascal. When we go up to a height of 16 kilometer approximately, then the pressure decreases to approximately 100 hectopascal. And then again, if we go up, maybe the next 16 kilometer, which is around 28 or something, then the pressure will be almost close to 10 hectopascal, 32 kilometers. So the next 16 kilometer, which is basically the 32 kilometer, the pressure decreases to 10 hectopascal or 10 milliliter. So basically, for every 16 kilometer, pressure decreases by an order of 10. Pressure decreases by 1 by 10 times the previous value. Decreases by 10 times the previous. So the first 16 kilometer, from 1000, the pressure becomes 100 MB. The next 16 kilometer, or from surface at a height of 32 kilometer, the pressure becomes 10, kind of like that. Now the vertical variation of pressure with respect to height. The vertical variation of pressure dP with respect to height dz is given by an equation known as the hydrostatic equation. Hydrostatic equation will give you the relationship between the variables dP and dz. So to see how dP and dz are related, consider a differential element of air of dimension dx, dy and dz. So let this be dx, let this be dy, and let the height be. Consider differential element and at partial like this with these dimensions. Now we know volume is given by dx dy. Now suppose this particle is present at a height z from the surface. If this is the surface, let this height be z. Let this height be z plus. So if the element is presented at an altitude of z from the surface of the earth, the forces that is acting on the element, this particular height, first one, right here, is a gravitational force, downward acting gravitational force. F is equal to mg. This downward acting. And in the opposite direction, the upward direction, there is a force known as the pressure gradient. What is this upward acting pressure gradient? We know that in the volume element dx dy dz, the pressure that is at this particular height is given by Pz, and at this particular height the pressure will decrease, and let this be P minus V. So at this level let the pressure be P, and at this level let the pressure be P minus V. I am subtracting because as we go up in the atmosphere the pressure decreases. So due to this difference in pressure acting on the top and bottom surfaces of the element, a net pressure force in the upward direction is acting on the object. Net pressure force in the upward direction is acting on the element due to the difference in the pressure acting on the top and bottom surfaces of the element. Due to the difference in the pressure acting on the top and bottom surfaces of the element, a net pressure force is acting in the upward direction. So the downward acting force Ng can be written as minus Ng, since it is acting in the negative z direction. And the upward acting force is due to the difference in pressure. So which is force is equal to pressure into area. The pressure difference is given by P dx dy, which is the pressure at this particular height, minus P minus dP dx dy. Okay. Now like if the two forces should be in equilibrium, should be equal for the parcel to be in equilibrium. For the parcel to be in equilibrium. We will get net force F plus Fy is equal to 0. Because Hg, or you can write P dx dy minus of P minus dP dx dy. It will be plus dP dx dy. Third term will be like that. P dx dy and minus P dx dy. Third term we will get dP dx dy minus Mg is equal to 0. Or you can write is equal to minus Mg. will be Fp equal to Fy or Fp minus Fg is equal to 0. Fp equal to Fg, which implies Fp minus Fg will be 0, or you can write dP dH dy is equal to minus mg. So mass is basically density into volume, right? Rho into d. Rho into, here the volume is dH dy dz. So the equation dP dx dy is equal to minus mg becomes equation dP dx dy is equal to minus mg, where m is equal to rho dx dy dz becomes dP dx dy is equal to minus rho dx dy dx dy and dx dy will go. It will be dP by dz is equal to minus rho g. This will be the final equation. dP by dz is equal to minus rho g. This equation is known as the hydrostatic equation. If an air parcel follows this equation, we will say the parcel is a hydrostatic equilibrium. This is the relation between dP and dz. So from this relation and the ideal gas equation that we just learned, we can find the pressure at a particular height z. So we know what is hydrostatic equation now. We also learned the ideal gas law for dry atmospheric air, which is P is equal to rho RT, where R is equal to 287 joule Kelvin inverse kilogram mass. Correct? So from these two, we can find the pressure at the height z. Okay. So hydrostatic equation is given by dP by dz is equal to minus g, and the ideal gas equation is P is equal to rho RT. From this we can write rho is equal to P by RT. If you substitute this in the hydrostatic equation, it will become dP by dz is equal to minus P by RT into g, which can be written in the form dP by P is equal to minus g by RT into dz. Now we want to find the pressure at a particular height z, right? So if we integrate this equation from the surface where the pressure is given by P0 up to a height z where the pressure is Pz, dP by P is equal to minus g by RT. Let's consider the temperature is not changing with respect to height. We will take T outside of the integral. We are assuming the atmosphere is having a constant temperature. From height 0 to z, dz. It will give you dP by P is having log P, P0 to P is equal to minus gz by RT. Or we can write log P0 minus log P, or log P minus log P0 is equal to minus g square by RT. So we can write, if we take exponential on both sides, it will become P by P0 is equal to exponential of minus gz by RT. Correct? by P0 is equal to exponential of minus Gz by RT. We can write P is the pressure at a particular height Z plus P0 exponential of minus Gz by RT. Since we are considering that T is a constant, this term G by RT will be a constant, which is known as the scale height of the atmosphere, which can be represented by capital H. And the equation reduces to T is equal to P0 exponential minus RT by G, not G by RT. So the term RT by G is known as the scale height of the atmosphere and is represented by capital H. So after substituting this, P becomes P0 exponential minus Z by H. So when Z becomes scale height, at the scale height of the atmosphere, the pressure reduces to 1 by E times the surface pressure value. So the scale height is the height at which the surface pressure reduces to 1 by E times its surface value. So we learned what is three different equations we learned. First is the ideal gas equation with the density P is equal to rho RT, R is equal to 287 joule Kelvin inverse kilogram inverse for 1 mole of dry atmospheric air. Second one we learned was hydrostatic equation, which is dP by dZ is equal to minus rho G. Third one is the vertical variation of pressure with respect to height, which is given by P is equal to P0 exponential minus Z by H, where H is equal to RT by G. H is the scale height of the atmosphere. As I said, since we are considering an isothermal atmosphere, we are assuming this for easy derivation. This is not the actual case. So since we are considering an isothermal atmosphere, where the temperature is constant along the whole atmospheric column. Suppose this value T is given by 260 Kelvin, which is approximately 'Suppose the temperature of the whole atmospheric column is given by 260 Kelvin. What will be the scale height? Scale height will be RT by G is 287 into 260 divided by 9.8, which will be approximately 0.0 1.6 kilometer. This will be the scale height of the atmosphere. If the average temperature of the whole atmospheric column is having a value of 260 Kelvin. So this is just an example that I gave. Now let's see the mass of the atmospheric column, the mass of the whole atmospheric column. So let's calculate the mass of the whole atmospheric column. How? Let's calculate the mass of the whole atmospheric column. So this per unit area. Let it be dm. We know that dm is basically density into volume, which is dx divided z. Since we are considering unit area, dx dy, which is the base area, will be 1. So dm will become rho dz, right? From hydrostatic equation we know dp by dz is equal to minus rho g, or we can write dp by g is equal to minus g dz. Since we are considering the whole atmospheric column, let it be from z0 to 0 is the height at the top of the atmospheric column. ZB will write. So dP will become P of should be minus dP by G. Okay. So it will become minus of P of Z minus P of Z0 divided by G, which will be here it will be rho dz or dm. Minus dP by G is equal to rho dz or dm. So minus of P of Z minus P of Z0 by G is equal to, so Z is equal to 0, which is the top of the atmosphere. Z0 is the surface. So P of Z will be 0. At the top of this atmosphere, the pressure will be 0. So the equation reduces to P of Z0 minus G. P of Z0 is nothing but the surface pressure, which is having a value of 1013.3 hectopascal by G. G is having a value of 9.8. So it will be 1013.3 into 10 raised to 2 Pascal by 9.8, which will be 103.4 kilogram per meter square. Or you can write 1.03 into 10 raised to 4 yeah, it will be 103.4 into 10 raised to 2 kilogram per meter square, or you can write 1.03 into 10 raised to 4 kilogram per meter square. This is the mass per unit area of the whole atmospheric column. Now, so this is per unit area. Now, if you want to calculate the mass of the total mass of the whole atmospheric column, what you can do is just multiply into surface area of the Earth, which is 4 pi r square, where r is the radius of the Earth. If you want to calculate the whole atmospheric column. Now, the next question. Yeah, one more thing I just wanted to say is the unit of the pressure actually. So generally in atmospheric science we use the surface pressure is actually 1013.15 hectopascal. This is the value of surface atmospheric pressure at sea level. So this is hectopascal, which is basically 1013.15 into 10 raised to 2 Pascal. Pascal is the SI unit of pressure. So whenever you are doing numericals, you need to convert the pressure into Pascal. So this is also equal to 1013.15 milli. These are just different units of pressure. And this value is 1013.15 hectopascal is basically equal to 1 atmosphere. Atmosphere is another unit of pressure. I just wanted to tell you about it now. The next question. The normal force per unit area that a fluid exerts on a surface. Force per unit, which is basically F by A. What is F by A? Is it called impulse? Is it called pressure? Is it called gauge pressure? Or is it called stress? Answer is pressure. It is having a unit of Newton per meter square. Pressure can't be expressed as. What are different units of pressure is a question. So we know Pascal is the SI unit. Newton per meter square is force by area. So Newton per meter square is correct. Pascal per meter square is not wrong. It is just Pascal. Then atmosphere is correct. Third one is millimeter of Hg. So generally we use mercury barometer to measure pressure. So how does a barometer measures pressure? As it will have an inverted tube on a dish of mercury. So when it is kept outside due to the atmospheric pressure, the mercury in the dish will start feeling some pressure. Because of this, the mercury will start rising through the tube. The height up to which the mercury rises is basically the pressure. That height gives you the pressure of that area. So that's why based on the height, of mercury, we define pressure. So millimeter of Hg is also correct. Hg is basically mercury. 1 atmosphere is equal to. So we already discussed the surface pressure. What is the surface pressure of Earth? That is 1 atmosphere. So 1.1013.15 hectopascal is basically 1 atmosphere. So the first question is 101.3 kilopascal. 101.3 kilopascal can also be represented as 1013 into 10 raised to 2 pascal, which is equal to 1 atmosphere. So this is correct. Second one is 760 millimeter of Hg. So when in the how much up to what height the mercury rises in the presence of at the mean sea level, what is the atmospheric pressure? So this is the figure of mercury barometer. So there is a dish of mercury in which there is an inverted tube which is present. So when air exerts pressure in the surface of the mercury in the dish, the mercury starts rising within this inverted tube. So the height up to which the mercury rises gives you the pressure. So 1 atmosphere when kept at mean sea level, the mercury rises to a height of 76 centimeter, as we can see from the figure, which is equal to 760 millimeter of 14.69 psi. So what is psi? So psi is basically pounds, pressure unit, pounds per inch. psi is pounds per inch. Okay, and 1 psi is basically 6894.76 Pascal. So how much psi is 1013 into 10 raised to 2 Pascal. So this is equal to 1013 into 10 raised to 2 divided by 6894.76. This will give you a value of the value will be equal to 14.69. So this is also correct. So all of the now this is a numerical. In mass, the mean atmospheric temperature is 200 Kelvin. Its gravitational constant, which is G, is 3.7 meter per second square. And Martian atmosphere is made entirely of carbon dioxide. So atmospheric composition is 100% CO2, right? We need to find the scale height H, which is given by RT by G, right? Where R is in, we need the unit of R in Joule, Kelvin inverse, kilogram inverse. We only know the value of R, which is 8.314 in Joule, Kelvin inverse, mole inverse. This is applicable for any ideal gas. Here we can't use the value 287 because this corresponds to dry atmospheric air, Earth's atmosphere. Here the composition is different. So the value of what will be the value of R in case of Martian atmosphere? It will be R by molar mass of the Martian atmosphere, which is 100% carbon dioxide. So it will be 44 gram per mole, or 44 will be 8.314. Let's just call this as R star. 8.314 is R star. We need R in Joule, Kelvin inverse, kilogram inverse. So to find that, we have to divide R star by 1 molar mass of Martian atmosphere. So 8.314 Joule, Kelvin inverse, mole inverse divided by 44 into 10 raised to minus 3 kilogram per mole. So the value will be 8.314 divided by 44 into 10 raised to minus value will be 188.95 Joule Kelvin inverse kilogram inverse. This is the value of R. Now since we know the value of R, we can calculate the value of G by now we know what is the value of R. We need to find H, right? So H is given by RP by G. RS we just got 188.95 into T. Temperature is given 200 Kelvin. 200 Kelvin divided by G. G is having a value of 3.7 meter per second square. Which will be equal to 10213 meter, or it will be 10.2 kilometer. I think the answer is correct. Can we just do the calculation again and just make sure I'm getting the right answer? I hope I haven't made a mistake. So you calculate by yourself and make sure that I haven't made a mistake. So the last question, the atmospheric scale height is the height over which the pressure decreases by a factor of. So we know P is equal to P0 exponential of minus L by H. So when Z becomes H, the equation becomes P is equal to P0 exponential of minus 1. So it will be P0 by P is equal to P0 by E. So P atmospheric scale height is the height at which the pressure decreases by a factor